This question reads, a battery with constant internal resistance is connected to a resistor of resistance 250 ohms as shown. The current in the resistor is 40 milliamps for a time of 60 seconds. During this time, 6 joules of energy is lost in the internal resistance. What are the energy supplied to the external resistor during the 60 seconds in the EMF of the battery? Well, I'm not sure the answer to that right now, but it sounds like a fun puzzle that we get to solve together. All right, so let's start to put some thoughts down here and see if we can't make sense of all of this. Probably do some calculations along the way. It gives us some space for working, but I like to kind of do my working up here on the figure. All right, so we've got the current in the resistor, so that's this one, is 40 milliamps. And so let's just sort of go around conventional current from positive to negative, even though there's probably electrons being repelled here going this way. Doesn't really matter. All right, so the current there is 40 milliamps. Let's call that I equals 40. And instead of milli, I'm going to write 10 to the negative 3. So we know there's that many milliamps, all right, in the circuit. So there's going to be 40 milliamps going through this internal resistor. We don't really know what it is. We just know it's constant. So that's R. This EMF here, let's call it E for EMF. Okay, and so that whatever number this is going to go here. And we want the energy supplied to this resistor. All right, energy that's supplied to the external resistor during the 60 seconds. It just tells us that there's 6 joules of energy that's sort of lost here. Okay, so we know the same 40 milliamps is sort of going through this. We know that that 40 milliamps times R would give us the voltage drop across this, right? So that's a voltage drop. That's the lost volts. Okay. Those are lost volts. We know that there is a terminal PD equal to the EMF minus those lost volts, but we really don't know enough to, or do we? So let's think here on this resistor. If we know the resistance R, and we know the current that's going through it, I, 40 milliamps, then what can we calculate from that? So we could use Ohm's law, say the voltage drop across this one is going to be IR. So let's calculate that and see if that doesn't help us. 40 milliamps current times 250 ohms of resistance. What voltage drop? Times 250. So I'm getting 10. $250 times 40 by 10, so that's -3. 10. All right, so 10 volts dropping across this external resistor. Well, that's got to be the terminal PD, right? So there's 10 volts of terminal PD means there was some EMF, and then we took away the lost volts here. And so we don't know what the lost volts are, but we do know the current was 40 milliamps. So 0.04 amps times R minus away from some E gives us 10. All right, note that we haven't yet entertained sort of this information, the 6 joules for 60 seconds. And so I think we're going to have to sort of rely on that now and maybe go to the definition of voltage. All right, and again, we're just sort of puzzling our way through this, just kind of thinking everything that we can kind of get out of this. All right, so if the energy lost in the external resistor is 6 joules, so energy divided by charge is equal to voltage. And again, that would be sort of the lost volts there. We know the total energy. And we don't know the total charge, but we can calculate it using charge equals current times time. So if we know that there are 6 joules of energy that are lost in the internal resistance, divided by how much charge? Okay, well, the charge is going to be the 40 milliamps, the 40 milliamps times 60 seconds, right? As they tell us, it's for 60 seconds, for a time of 60 seconds during this time. So it's the same 60 seconds when we lose 6 joules that these 40 milliamps were going through the external resistor. So now we have our 0.04 times 60, and that gives us a charge of 2.4 coulombs. So just kind of keep track of what are we solving for when we do this. You can see that 2.4 is the answer of joules and voltage of EMF, but it happens to also be the charge here. So 6 divided by 2.4 coulombs would give us the lost volts here. Because remember, this is voltage is energy per charge, and we know that this is the energy lost in the internal resistance, right? And so that, by definition, is sort of the lost volts, right? The internal resistance, lowercase r. This was the claim that we reached last week with our lab work. So 6 divided by 2.4, 2.5. And so now we know this term here. So we have the EMF is something minus 2.5 lost volts gives us the 10 volts we've already calculated that we know is the terminal PD, because that's the V equals IR voltage drop across this external resistor. There's 10 volts available sort of to the external resistor to drop, but there was how many volts to begin with? Well, this gives us 12.5 minus 2.5 would be 10, but that's obviously, oh no, wait, yeah, that is an answer right there, right? EMF. Okay, so we get 12.5 minus 2.5 equals 10 volts. So that checks out. That gives us an EMF of 12.5. But now it says, what is the energy supplied to the external resistor? So if we're getting an EMF of 12.5, there's no ambiguity here in these answers. You know, it's got to be 24, right? Unless we made a mistake here. So we might reveal a mistake if we get some other energy, you know, besides 24. But the energy supplied to the external resistor, let's think about energy different ways here. So energy per time is power. So we could maybe calculate the power here, you know, because we know the current, we know the resistance, so we could use something like I squared R to get power, calculate the energy because we know the time is 60 seconds. So we could kind of think about this as like the energy in the external resistor is power time. What's the power? Well, I squared R, right? So this kind of reminds us, here's a good equation for power. If I've got 0.04 amps or 40 milliamps, that's 0.04 amps squared times the 250 ohms of resistance. And so I can calculate using I squared R, there's 0.4 watts of power in this resistor here at that current, at that resistance. And so now I know what the power is, 0.4 watts. If you multiply that by 60 seconds, watt seconds are joules. So 0.4 times 60 is sure enough 24 joules. Confirming choice D is the correct answer to this. This has been a fun puzzle that we've got to solve together. We'll see you next time.